Good morning everyone. I am Yatin Shankar Narayanan and today I will present my project, The Effect of Different HBMs on Restraint System Design. Human body models like GHBMC, THUMS, and SAFER provide greater insights into occupant kinematics and injury risks than what crash test dummies can. However, these models have underlying differences in their geometry, posture, and materials. So the question arises, do these differences impact the optimal restraint system design? The major objectives of this project begin with morphing the HBMs into a common geometry to enable comparison. The study will then be extended to include diverse occupant profiles, followed by case-specific optimizations to understand if the restraint system is sensitive to the HBM chosen. Let us take a look at the postural overlays between the baseline HBMs. Now, let us see what they look like when they are morphed into identical mid-sized male geometry. Now let's see how the postures compare. So we see that morphing reduces the postural differences and improves the comparison. Let us now observe the kinematics. All simulations were run with HBMs as drivers in a Toyota RAV4 model, and we see that the morphed models are more consistent with each other in terms of the kinematics. This is further justified by injury trends across morphed models which are more consistent than what we see in the baseline versions. This provides a good starting point to expand the occupant study. In addition to the mid-sized male, we now include the small female, small obese female, large male, and large obese male. When dealing with different occupant sizes, it is critical to scale the injury risks. These typical injury risk equations shown here do not consider the size of the occupant. This means that scaling factors need to be included before proceeding. In the interest of time, I will talk about how I did this for the femur. First, I chose common locations for the cross sections across the three models. Then I observed it close up. And finally, I strategically chose nodes to harmonize the cross-sectional areas across the three HBMs. The average area becomes the scaling factor, in this case 1029.17, so the updated equation for the femur injury risk looks like this. Repeating this for the chest and tibial regions gives us this set of modified equations which we can then use to compare the models. It is important to note that all simulations are run under identical conditions with baseline restraint system. Let us now analyze the kinematics and injury trends in the small female. We see that chest injury seems to dominate while the head injury is not a concern. This is because the airbag prevents a strike through, as we can see from the kinematics on the slide. Now, in case of the small obese female, we observe similar trends, except the lower tibia now becomes dominant. And this makes sense as obese occupants are at a greater risk of submarining. Here, head injury is still not a concern because of prevention of strike-through. The large male, however, shows a different trend when compared to the small female and small obese female. The head injury now becomes a major concern. This happens because the baseline airbag cannot prevent the head from striking through and hitting the dashboard, as we can see from the kinematics on the slide. Finally, in the case of the large obese male, we observe an interesting trend. Here, both the head and lower extremities have great concerns. This means that the restraint system optimization in this case could be quite challenging, and I'm very interested in seeing how that turns out. Taking a look at the injury risk trends across different body regions as the occupant size changes, we see similar patterns across GHBMC, THUMS, and SAFER with some outliers. This forms a strong base to begin the optimization studies. I would like to conclude by stating that morphing improves the postural differences and harmonizing the injury risk scaling enables better comparison across the models. I am currently conducting subject-specific optimizations to study how sensitive the restraint system is to the HBM. Following this, I will build response surface models to predict the results without requiring additional simulations. I would like to thank Professor Jingwen Hu for his continuous support and guidance, and I also want to thank Kyle and Yangshin for their help in various aspects throughout the project. Thank you so much for listening to this presentation.